Hi, this is Dr. Liu. In this video, we'll explain how to do freefall problems. I have here two copies of my constant acceleration motion equations and parameters. Because freefall is a special constant acceleration motion, it should also follow the same formulas, except that some things will have to change. For example, the acceleration here will be fixed due to gravity. And let's set up our axis. So we have an origin with an x. Although we use y for vertical, this time we just use x. So our axis points upward, and gravity's acceleration is downward. So this is acceleration due to gravity. So this value will be a negative quantity, and we'll replace it with this. We'll say that we'll define the g equals 9.8 meters per second squared. This is an accepted acceleration at the surface of the Earth. Because it's downward, we'll use a negative g. So a acceleration is negative g, or negative 9.8 meters per second squared. So that's the only thing there is to free fall. So we'll just erase this, and we'll erase that. We'll say that instead of having 6 parameters, now we only have 5, because our acceleration here has been specified as minus 9.8. So I'll put a negative g, negative g. So this is our constant acceleration motion under gravity, or the free fall problems equations and parameters. So let's just remember that g here, as any physics quantity is defined, is always defined as positive to avoid any confusions. So to say that we're accelerating downward, although we're setting an axis upward, is our acceleration is negative g. So don't try to switch signs. If somehow, say, your problem didn't resolve in a reasonable answer, you thought, oh, maybe I had g backwards. No, if you have it with an explicit negative here and a positive quantity, then you didn't have it backwards. It may be something else. Okay, so I have an example question. So this is from University of Physics, published by OpenStax. It's from chapter 3, question 69. A rescue helicopter is hovering over a person whose boat has sunk. One of the rescuers throws a life preserver straight down to the victim with an initial velocity of 1.4 meters per second, and observes that it takes 1.8 seconds to reach the water. Question part A, list the knowns in this problem. Okay, we like that. We also list unknowns. Part B, how high above the water was the preserver released? Note that the downdraft of the helicopter reduces the effects of air resistance on the floating life preserver, so that an acceleration equal to that of gravity is reasonable. I like this because otherwise, if you're just throwing something down, maybe a feather, maybe not a life preserver, but a feather, and then it wouldn't really fall entirely under gravity. It would be affected a lot by air resistance. So I like the fact that the authors wrote this into the question to make it reasonable that only assuming gravity is going to work. So let's follow the questions step. Just list the knowns and unknowns, right? So we have this equation right here, and why don't we get the list? Okay, so here, copy. Let's see if I paste here, what's gonna happen. Okay, I think I still can move it. That's great. Alright, so let's see what happens. We have the initial position, final position, initial velocity, final velocity. Since the rescuer threw the life preserver downward, right, this is going to be a negative velocity because we set up this customary axis to point up. So this velocity is going to be a negative 1.4. 1.4. And the final velocity when the life preserver reaches the water surface is unknown. You might think that it is 0, but that is only after it has impacted the water surface and maybe just float a little bit before it actually stops. So we're just talking about right before the life preserver hits the surface, it was still under just gravity. And the time it takes is 1.8 seconds. Okay, so apparently we have too many unknowns. We have 3, and we only have these 2 equations to solve. So looking back at what we have done in the past, we are free to set up our origin of the coordinate system. So maybe we can do that, right? So in this question, because of the starting point is what we can set as the origin, I like to draw the axis maybe a bit further down with the origin a bit further up. So let's do this. So we'll place the origin right here, and this is where the life preserver was thrown. So okay, life preserver. Okay, so it was thrown downward, and here's water surface, and someone's basically swimming, trying to stay afloat. And let's put a log here. Okay, so this maybe a plank. So this guy is not immediately dying yet, and the life preserver is going to strike the water surface, hopefully not on the victim. So that's sometime later after 1.8 seconds. So this position will be the X position, the final position, and the life preserver right here is moving downward. So it has a velocity v downward, and it has a velocity v0 here when it was first thrown by a rescuer. Okay, so now we can say that the initial position can be set as 0 because we're free to choose where the origin is. So now we only have 2 unknowns. Let's go ahead and try to solve them. Let's partition our space. Alright, so with equation 1, final position is initial position plus initial velocity, negative 1.4 times time, 1.8, minus 0.5. G is a positive quantity because the negative is already explicit. This is 9.8, then times time, 1.8 squared. So we can already get the position. This is the absolute position. So if we just want the height here, this height is the absolute value of this coordinate, which is below the 0 where we set this origin is here. So let's sort out the terms. Minus 1.4 times 1.8 minus I like to just combine this because we do it so often. Half of G, 9.8 over 2 is 4.9. So you may as well just get used to this numerical value of 4.9. Okay, so now we can use our calculator. Just calculate this value out. Let's move it aside. So negative 1.4 times 1.8. and then minus 4.9 times 1.8 squared. I really like Python because on the numerical keypad, which is what I have next to my tablet, I don't really have a caret sign to do the typical square, and the times works perfectly. So we have minus 18.4. If I round it to the digits, we only have 2 digits, right? So we'll actually round it to minus 18. Let's hide that. Minus 18 meters. So basically the height, as right here, the height is the absolute value of x is 18 meters. All right. So that is how high above the water is, 18 meters. All right. So there's one other equation here that we didn't even touch. So why did we even not need that? And that's because we were not asked how fast the life preserver was going to strike the water surface at. And this may be important because if you throw it, yeah, you're trying to rescue the victim quickly, so you threw it, but that also makes the life preserver strike the water surface at a higher velocity, and possibly injuring the victim. So maybe we should find out how fast the life preserver is hitting the water surface, although it's not asked. So let's do it. Well, okay, let's put 1 here, and equation 2, velocity is initial velocity minus 9.8 times 1.8. Let's get the calculator out, move it to the side, minus 1.4 minus 9.8 times 1.8. This is going to be a negative velocity. Okay, minus 19. Let's keep 2 decimal places. Minus 19 meters per second. So minus 19 meters per second. And this is actually going to be hurtful if it hits the victim. So hopefully the victim is not very near the life preserver, but close enough so they can just swim up to the life preserver. But given a plank I just gave that to that victim, maybe it's best just to hoist this person up. Alright, so now what we did was I showed you one particular example of how to do free fall. Free fall is actually easier than the constant accelerated motion because it has this one last unknown, right? We don't need to know find the acceleration because it's already given to us by Earth's gravity. There could be chances that we can talk about maybe something happening on the moon, on Mars, or some other planet X where this is unknown. But near surface of Earth, this is a fixed quantity, and we usually point our axis upward so that it's typical that any positive velocity is traveling upward, negative velocity traveling downward. And we use these explicit negatives to express the downward gravitational acceleration, so that these g values, any physics quantity is defined as positive, no negatives. Even with charges on electrons carry negative charges, we define positive charges, and then we put negative in front of that charge quantity for electrons charge. Thank you.